Well, let's show a video first, sure. Everybody likes now. So if you pay close attention, look for the rabbit down here on this next one. Hold on. Wait for it. So no rabbits were harmed in the making of that video. As you can see, our rockets move a little quicker than the Delta that Abe showed you. The Delta's not cool, but ours really get up and go.
Is that White Island?
That is actually White Sands Missile Range. Yeah. Okay, so my name's Ted again, and I'm a research and development engineer. As far as I can tell, there are sort of three kinds of astronomers. Now, you'll have to forgive my generalizations, but there's theorists, and they like to stare at computers and think about astrophysics. You've got observationalists. They like to, take data and look at objects through telescopes, or maybe electronic telescopes, whatever. And then you have instrumentalists, and instrumentalists like to build telescopes, and that's where I fit in, because I work alongside an instrumentalist. Professor, he or she, maybe comes up with a neat idea for a new instrument, and then they give us a pie-in-the-sky idea, and somebody has to figure out how to actually do it. So that's where I fit in. I'm supported by my wonderful family who's sitting at that table, and my youngest son was providing the soundtrack for Abe's talk, so if you heard some baby screaming, I apologize. That's right. Okay, so before I worked on rockets, I did some boring stuff. Has anybody here ridden on a 787? Anybody? Oh, then your butt has been supported by my C-track pedestal here. So,
Thank you.
You're right. So it was not a super exciting job. I also worked on, there was some people who thought that air taxi was going to be a thing. Yeah, they were huffing. And that didn't turn out to be a thing. But that's what I did before rockets. And since I started working on rockets as an undergrad, and then I left undergrad and worked for aircraft industry on composite structures. And then I've worked on rockets ever since then, almost from 2006 forward. So these are some of the patches for the rockets that I've worked on. There's been a whole bunch for many different universities now. I'm on 3 different universities. I'm doing pretty good there. Penn State is my latest home. And this is our last launch, this water recovery one, and then this was the one previous. Chess was actually a mission that launched on the same campaign as our water recovery rocket, and I worked on that one too, which was kind of weird because I helped build it, and then I didn't work for them for many years, and then we actually ended up on the same small island in the South Pacific, launching the same rockets together again. Okay, so Abe did a great job talking about this. Astronomers love light, and they come in many different colors and energies. I'm gonna skip this. Everybody knows about Hubble. Everybody likes Hubble. Hubble's great, does lots of cool stuff. Hubble sees in ultraviolet all the way up through infrared. It's been upgraded many times. It's an incredible instrument, doing lots of cool stuff. Not as many people heard about Chandra, but why do you need to go to space? And Abe actually mentioned this as well. Most of the ionizing radiation, so we consider it light that's sort of ultraviolet above ionizing, and that means that it can actually ionize atoms, knock electrons off. It's good that it doesn't make it to us because it can actually damage your cells, it can damage your DNA. Now, your body's used to it because we're getting blasted all the time, and you can get UV rays and you need it to make vitamin D and this sort of thing. But in general, we should be very happy that the atmosphere is doing such a good job blocking most of this from us. So this neat picture here kind of shows you what wavelengths of light make it through the atmosphere. And you'll notice that X-ray light doesn't make it at all. It's just completely blocked. So you have to go to space with it. Now, Abe, again, did a great job of explaining a lot of these objects, and I've even used some of the similar pictures. And here's our glorious Chandra Space Telescope that nobody seems to know about. Everybody knows about Hubble, but only the X-ray astronomers know about Chandra. Chandra's incredible for a lot of reasons. I personally think it's really cool. Sort of the backstory of Chandra is that it was launched by the first female shuttle commander. Her name was Eileen Collins. She was also the first female Air Force test pilot. It's pretty incredible. It was also one of the heaviest things that the shuttle ever launched. And wrap your head around this for a second. It was like this was a rocket motor inside of the shuttle. So it was actually kind of a high-risk mission because if that rocket motor had a problem and it's inside the shuttle bay when the shuttle's launching, you would get a very interesting show and a lot of very public funerals. So it was a really incredible mission. This thing is absolutely massive. If you've been to any of the Air and Space museums like the Hazy, the space shuttle is huge, and this thing's the size of a school bus. It's a really incredible instrument. Now it is getting pretty old. So as Abe mentioned, you probably, if you're an astronomer, you want the next best thing. been up there a long time, and that's sort of where we come in. We're trying to improve these new technologies. So let's talk about low-cost access to space. So Congress likes to be stingy and not give people money to make cool science instruments. And NASA is also very risk averse. So NASA has to ask Congress for money, but they don't want to ask for money if they know it's not going to work. So they've come up with this whole system called a Technology Readiness Level, TRL. And every technology that you want to fly, be it maybe one of Abe's new detectors, a hybrid CMOS detector, or even a new mirror type that you've never launched before, you're going to have to prove to NASA that it's ready to go. It's in prime time. It's going to function perfectly in space. And before you're going to get $10 billion to build the next Chandra Space Telescope. So basically, this is where my entire lifeblood, this is what I do. We come up with new ideas. We build stuff that's low TRL, for not very much money. It's high risk, high reward. In order to launch things cheaply, you also need cheap rockets. SpaceX rockets, while getting cheap, are not particularly cheap. We're talking, on the order of a few $1 million to launch something into space for just a very short amount of time. All right, how do you do that? How do you do that? Well, you come up with this idea called the NASROC. NASROC stands for NASA Sounding Rockets Operational Contract. This is the NASA group that we collaborate with to launch these small suborbital rockets. And let's go through sort of how they got started. This plot is kind of humbling and makes you also a little bit, it's incredible. This is millions of dollars, and this is how much money they're estimating to complete James Webb, right? So this is, $400 million that year in financial year 2010. This is fairly out of date, but James Webb's going to end up costing something like $10 billion when they're done. And boy, I am crossing my fingers that it works, because if it doesn't, Congress will never give NASA a huge chunk of money again, probably. So let's hope it works. But yeah, the big missions eat up all the money, so we have to do everything on the cheap. All right, so step one, you want to make a rocket program. Well, first you have to have rockets. These came from a long time ago. The Chinese were building rockets way, way back, almost 1,000 years ago. This is actually called a fire arrow, and it wasn't technically a rocket. It was more like a fire charge on the end of an arrow that you launched. Those evolved. This is a Korean thing that was taken from the Han Dynasty called, I'm going to pronounce this wrong, but this is called a Hwacha. If you've ever seen the Mythbusters episode, they made one of these. These are basically rocket-powered arrows that they launched out of a battery, like 100 at a time. Pretty incredible. So rockets are not particularly new, but of course, like any other technology, they developed over time. Here's Robert Goddard launching his first stuff, and then you really got going kind of with World War II and the Nazis doing the V2 rocket. So this is a cutaway of a V2 rocket, and of course we snatched up all their best scientists right at the end of the war, and that sort of started the American rocket program with a whole bunch of technology developed. So step one is you got your Cold War. So I don't think that as a young person I could truly fathom the amount of money that was getting spent on the Cold War, but it was incredible. And the amount of technology that was being developed both during World War II and just after World War II is unbelievable. I mean, this runs the whole gambit from nuclear weapons, intercontinental ballistic missiles, solid rocket motors, et cetera, et cetera, et cetera. So this pace is crazy. So this is the first working ICBM. It's called an R7. It was Russian. And this is an interesting graph. I know it's hard to see. It's very small. These are launches of all of our early intercontinental ballistic missiles, and all the pink ones are ones that failed. So you can see that in calendar year 1960, they launched almost 20, right? And that's just ICBMs. So it's pretty incredible. The amount of money being spent, again, just incredible. This also transfers into solid rocket motors and surface-to-air missiles. So you got some fast jet airplanes being invented right after World War II. Again, the Germans had the first jet engine, and then it just spitballed from there. That makes anti-aircraft guns worthless. You got fast jet bombers with nukes. You need standoff weapons. You need missiles that can hit the bombers before they can blow you up. You need missiles that can be launched from ships that are able to hit the airplanes before they launch their anti-ship missiles. So you've got a ton of development for missile technology. So this is called a Terrier missile. They started production in the early 1950s. They made 8,000 of them. This was a beam-riding missile. So they aimed a radar beam at the enemy aircraft, and the missile basically just followed the beam all the way to the airplane. They made 8,000 of them. They probably launched, 50 to test them, and then they sat, and then they eventually became obsolete. Why is this awesome for NASA? Well, all of a sudden you have all these rocket motors sitting around with nothing to do. Same thing goes for this thing called the Talos. These were also, I didn't mention this, there's this whole military operation called Operation Bumblebee. And they were basically developing all these new missile technologies. And both the Terrier and the Talos were developed out of this program in the early 50s. Alright, so we've got a ton of rocket motors. Again, they made 2,400 of these, probably launched 100 maybe total. Spent a ton of money, and then at some point they just gave them to NASA and said, hey, you can have all these if you store them. So it goes, okay, so that sounds good. So NASA takes these, and NASROC says, okay, cool, we got all these surplus rocket motors, and we're going to use them for something cool now. We're going to recycle them into a peacetime mission of launching science. So this is the current NASROC stable, and these little numbers here, they just have different numbers for vehicle configurations. The one that we always fly is called a Black Grant 9. This is a Terrier first stage. These are all solid rocket motors, mind you. And this is a Black Grant second stage, and then here is all the payload portion, including the telescope and a bunch of NASA components. And you notice that, you get a whole bunch of different configurations. This is like a 4-stage. This is like a Talos, Terrier, Black Grant, Nika. You notice the upper stages on those don't even have fins because there's no atmosphere. That 4th stage motor lights when they're already in space. So there's no point in having fins on them. So all these different configs. Cool, all right, well, awesome. This is a cool plot showing, this is how high you get, this is how heavy you are. It kind of makes sense. If you're heavy, you don't go as high. And this is how much time you get above 100 kilometers, which is sort of a rough idea of what we call space. Cool story, Ted. Why do you care about this? Well, you want the best bang for your buck, so you want to launch a big, heavy payload as high as you can for as long as you can. So I know you guys are thinking, all right, cool, so let's, Penn State, we're going to build our telescope, we're going to put on this thing 4 stages. Well, about that. The problem is you don't have very many places to launch these things out of. And if you use one of those big 4-stage rockets, there's really not very many missile ranges that can actually accommodate it. So this is White Sands Missile Range. Who here's been to New Mexico? Anybody? Who here has been to White Sands, New Mexico? All right, it's an incredible place. I highly recommend getting out there if you can. White Sands is this huge government. I think it's actually owned by the Department of the Navy. Again, it's kind of weird, the Navy owning a bunch of land. But it's this huge missile range. There's no people on it. And we launch our rockets at the south side, going north. It's pretty narrow. And our rockets go up, and then they come back down. That's great. But this limits the size of rocket that you can launch, because if you get any bigger, it'll go off the missile range. This also dictates that you have boost guidance. I'll get to that in a second. In fact, I'll pass around my fin now. So this is a fin that's actually been in space from the boost guidance section of a rocket that's flown. So please touch it. It has been in space. It's pretty incredible. It's made of magnesium, and this is what steers the rocket on its way up to keep it basically on the missile range. So take a feel. The front tip is actually made of a high-strength steel alloy, and that's because it gets really, really hot. And then wrap your head around that you're steering a rocket while it's spinning at about 10 times per second. So that fin can... Yeah, there are 4 of them, yep, but I only got 1. Yep. All right, so where else can you launch these things? Well, here's some of the locations that we launched on. So we've got White Sands, New Mexico. We've got Poker Flats, Alaska. We've got Wallops Island, Virginia. Now that's nice, you launch into the water. But what if you want to look at a target that's in the southern sky? All these locations are in the northern, they're basically in the northern hemisphere. So if you want to look at a southern sky target, you can't launch it. And that's where Kwajalein comes in. And that's where we launched our last rocket from. Now, Kwajalein Atoll. Now this is a tiny little island. It's part of the Marshall Islands. It's actually owned by the U.S. military. And there's some huge radars. It's been, it was basically conquered from the Japanese, and we never really gave it back. We lease it from the Marshallese for probably a pittance or something, but it's basically a big military base. This is nice because, first off, there's not a lot around it, so you can launch big rockets, and it's southern sky, so you can access targets in the southern sky. Interestingly enough, NASA had never launched a telescope like ours from a water-based location like this. So we were actually testing some of their technology at the same time with our technology. And I'll get to that in a second. Okay, so here's this last rocket. Here's Kwajalein Atoll. So probably a lot of you don't necessarily know where Kwajalein is, because why would you? It's near Australia. This is Australia down here. It's a coral atoll, which means it used to be an island, and most of the island has sunk into the ocean, and all that's left is kind of this barrier island. And then we were actually on one called Roy Namur, which is this tiny little island up on the northern part. You can see the whole island is basically a runway and a few buildings. I mean, there's literally nothing. There's 50 people on it year-round. and then we, quadrupled the population when we went there with our entire team of 120 some odd people. It was a really neat experience. I'll show some pictures, but this is where we're launching from. The launchers are actually right out here in that little building right there. So, let's talk about the parts of our sounding rocket. Now, I already talked about the motors and how they're military surplus. I don't have these on the diagram here, but the first stage is here and the second stage is here. Now, for a sense of scale, these things are about 60, 70 feet tall. They're quite big. And then you've got some other parts. So I'm actually going to go from the front end back. So our rockets have parachutes, so these are suborbital, meaning they go into space, but it's just like if you fired a gun straight up, it's going to come back down on a parabola, and in theory, if your parachute goes, you're going to get it back. They don't have enough horizontal velocity to go into orbit, and you probably wouldn't want that anyway because none of our stuff's designed to be in orbit. So, we're not that hard, we are not thermally controlled. If the payload got stuck up there, bad things would happen, we'd freeze or whatever. And we're only up there for, basically 300 seconds of data. The next section is a piggyback ACS tank, so they use gas to steer this thing around. So most telescopes on the ground, you have electric motors that can steer it to point it at the star that you want. Our telescope actually has little gas jets that can fire and slew the telescope around. So at the end of it, I'll show you a neat video of that. But there's gas in there, high pressure gas. It's actually argon, and they use it because argon's heavy, real heavy, and it's also inert, so you don't want to huff something that's bad for you. Non-toxic, it's just heavy. Xenon would probably be better, but it's expensive. But I think argon is the heaviest, cheapest thing they can get. The next section is, section 3 is the attitude control system. So this has gyroscopes and also all the electronics for the star tracker. Section 4 is the telemetry system. So we don't actually store any of our data on board from our camera. So Abe's detector is snarfing up those X-rays. There's not very many, maybe just a few per second. And we're turning those into electric signals and we're sending them down via a radio link real time. So we actually don't store any of the data on board, and that's nice because if for some reason our rocket splashes in the ocean and gets lost, then we still have our data and we're happy. The next section is section 5 was it's a non-hermetic section where all the umbilicals came in. So this is where all the payload umbilicals, and then when I say umbilicals, I mean these are things like electrical connections that you want on the launch rail, and then when the rocket launches, they pull off. And you've seen these probably in videos when the space shuttle launches, things pop off and then swing out of the way. We have the same thing, except it's much more crude. So that's where all those came in. Our electronics lived in section 6, and then our telescope was in this big, long section. Just like Abe said, you can't bend the X-rays very much with those parabola, hyperbola mirrors. So you have to have a long telescope because the X-rays don't like to bend. So you need a really long telescope. Most of this is just empty space. We've got some balance weights, and then you have the water wedge, which was a piece designed to pierce the surface of the water so you don't belly flop and destroy your shutter door.
What's the focal length?
I'm sorry?
What's the focal length?
The focal length of this is about 3 meters, approximately. Yep. So it's pretty long. And last but not least, you got the second stage igniter on the last section. Well, let's talk really briefly about our science. Again, Abe talked a lot about this. I'm just going to gloss over this. Spectroscopy, when you take the light and you break it up with a prism, you get colors. There were a couple pioneers in this field that realized something was going on. Now, they didn't fully understand it, but you got this guy named Fraunhofer. He was kind of an interesting fellow. He was actually almost like a child slave. He was working in a glass factory when he was really, really young. He almost died in the glass factory. He met some prince after the glass factory disaster, and the prince basically said, "I'm going to send you to college. You seem like a bright guy," and sort of started him on that path. And he ended up taking one of these early prisms and looking at the sun and saw all these dark lines in the solar spectrum. He didn't really know what they were, but this was like the starting of spectroscopy. And then this guy named Secchi, he took it even further. He's looking at different stars and noticing that each different star had different dark spots in its spectra when you break up the light with a prism. And this is sort of where spectroscopy started. So we're not making pretty pictures. We're taking the light and we're bouncing it through a prism, and we're getting different elemental fingerprints, right? So carbon makes a fingerprint like this. Now you can do this experiment yourself. If you get one of those little mylar, physics departments often do this, and you hold it up to a fluorescent light, you'll see that spectrum. You hold it up to, maybe you get a tube of neon, you'll see the neon spectrum and all those spectral lines. We are doing the exact same thing, but in X-rays. So we take the X-ray light, we bounce it off a grating, which is basically just an X-ray version of a prism, and we spread out all the colors, and then we look at it. So here was our target. This is called Vela. Again, Abe sort of talk to you guys about these. This is a supernova remnant, so this is a star that blew up a long time ago. They think about 12,000 years. It's really large on the sky. So what's kind of neat is I put the moon, that's how big the moon is on the sky. So this little dot here, so you can see this object, you can't see it with the naked eye, but it's huge. I mean, it's absolutely huge. Our instrument is sort of... So anybody who plays video games knows that current consoles and video game systems keep pushing this higher and higher pixel counts. The same thing goes for your digital camera. You know, you get to start seeing detail that you wouldn't see when you get more pixels. The same exact thing happens for astrophysical spectra. Now, I know this looks like not a rainbow, but it's really an X-ray rainbow. It's just that these X-rays are less energetic than these, right? So these are redder and these are bluer. And we're splitting up the colors just like we did in the prism. The better resolution you get, you know, if you have terrible resolution, all you see is a blob. You say, hey, look, there's light there. I can't really tell what elements are there. As you start increasing the resolution, you start able to, these elements are making these lines, they're just blurred out. So you can start seeing these crazy lines, and these, again, I'm not an astrophysicist, but the astrophysicist can tell you, hey, look, I can fit a mathematical model of this, and this is carbon that's this hot, it's 5 million degrees, and it's moving at these rates, all from these lines. So this is where a lot of the science comes from, these spectral lines. So we want to push X-ray resolution as high as we can get. So here's our whole rocket. Here's the first stage, here's the second stage, here's our telescope. Right, so this is the portion that we build here at Penn State. So I'm gonna zoom in on that. So this is a CAD model, I'm gonna talk about that in a second, but this is our whole instrument. This is called the collimator. The X-rays come in through the shutter door. We also call it the toilet seat because it kind of opens very nicely like a toilet seat. The X-rays then come in through the collimator. The collimator is like basically a crappy version of a telescope. Because X-ray mirrors that Abe talked about are very expensive and hard to make, we used a different method where we basically have a series of screens, and you can imagine these screens having smaller and smaller squares. Only the light coming to a focus at our detector can actually make it through all these screens. So, imagine lining up 50 screen doors. If you get your eye in the right spot, you'll be able to see all the way through. But if you're off a little bit, you won't get any of it. Now that's cool because it's cheap, but it's bad because it blocks most of the light. And that's exactly what you don't want in a telescope. You want to gather light. You want to focus light. This is kind of a subtracting method for focusing light, but it was cheap, and that's good. The next thing the X-rays bounce off is called gratings. I talked about these. These are basically the X-ray version of a prism. We make these at Penn State. I know they don't look like much. This is actually a scanning electron microscope image of one of these things. Looks like little saw teeth. These are incredible. These are state-of-the-art. I mean, we are in the Millennium Science Building, the weird building with the crazy cantilever on campus. They have tooling in there, and we use similar techniques to how you make computer chips to basically manufacture these large gratings. So this is about 100 millimeters by 100 millimeters, so that's, it's about this big in real size. And we're putting thousands and thousands of these features across the face of it. I think it's like 10,000 per millimeter.
Is it like grating?
It's a grating. That's exactly what it is. Yep. And of course the light comes in and bounces off these, and it does interference, and you get different colors out, and you get a little X-ray rainbow. But this is really incredible, and we're able to do this all in-house at Penn State. Wow. And I can say pretty confidently that the stuff we're making here is way better than the stuff on Chandler, which is kind of crazy because we make them.
You give tours?
Absolutely, yeah, absolutely. In fact, come to AstroFest. We did a lab tour last year, and it was very popular. All right, so the lights bounce off our grating. Now we got our little X-ray rainbow, and then I think you've seen this picture before from Abe's talk. That's Abe's baby, and some of the members here of his group are sitting in here. So they do the detector work, right? So we put our X-ray rainbow on their detector detects the light, and then it goes through all of our electronics and gets telemetered to the ground. So as an engineer, I wanted to mention that, thank goodness that I have some really incredible tools that I get to work with to make my job easier. One of these is called SolidWorks. So before we even start building a rocket, we can design the entire thing in a computer before we even cut the first bit of metal. So this is an example of a SolidWorks screen capture I made. SolidWorks is this incredible program. There's several different ones on the market, but we use SolidWorks. I can model parts in 3D, and then I can take a file and I can just send it to a machinist, and he or she can then turn that computer file into a physical part for me. And that's basically what we do all the time. Oops, I went forward. I'm sorry. The next thing we use is another tool called Altium. So we make custom circuit boards, custom electronics all the time. Same thing. You got a really incredible software package. This thing does a ton of the hard work for you. This is actually the printed circuit board from an iPhone. Components keep getting smaller and smaller. I don't know if you've seen a modern circuit board, but the components are getting to be so small that you have to wear magnifying glass or like grains of sand. It's incredible. This software takes a lot of that work out. You draw schematics. and you can actually put all the components on the board, and it'll route all the connections, and it's incredible. So I get to use those tools, which is really helpful.
So you guys design it on campus?
That's right, yeah. So our portion, you know, the telescope and all the telescope electronics is all designed in-house at Penn State. But of course, we collaborate heavily with NASA. NASA Wallops is the group that we collaborate with, and they build all the other parts, and they have their own, you know, solid models of all their bits. You know, so the attitude control system they build, and you know, telemetry systems they build to suit our needs, et cetera, et cetera. So the next thing I have is a whole bunch of pictures, and I'll just kind of talk through them. So this is our instrument. You'll notice the date. This is like right before Thanksgiving. This is sort of when we finished, right before we were going to ship it to Wallops. And we were going to ship it to do what's called integration. So that's kind of what it looked like, the chunk that we built in-house. That's in our lab. Then we put it in a box. Surprise, surprise. Then we put the box in a U-Haul. And then we drove to Wallops. Now, once we got to Wallops, this is a ground station. So in the ground station, they basically have an entire setup of the receivers. They even have little, you know, miniature antennas. So basically, we're going to bolt all the sections of the rocket together, all the pieces that we built, all the pieces that NASA built, bolt them all together, and test them as a unit to make sure everything works like it's supposed to work. This is a long, tedious process, but you can see here's our telescope, here's the telemetry system, these little gray bands are the antennas. This little black block here is a gas jet for roll. So it actually comes out and it sticks sideways, so if you want to roll the telescope like this little gas jet here squirts. This is the nose cone, and basically the parachute would go in that hole along with the flotation. So we go to Wallops and we start putting the thing together. And that takes a long time, and we test it, and they document everything, so they even, you know, they take pictures of all the connections you make, so we're hooking up the connectors and all this sort of thing. Then we do what's called environmental testing, so we take the entire rocket and we put it on essentially a giant electromagnet, and we shake it just as hard as it's going to get shaken during the rocket motor burn. And that's about 17 Gs, so if there was a human on board these things when they launched, they would die, and they would just get turned into a little pellet at the bottom. So we shake it to make sure that it's not going to break. And of course, we've spent a lot of effort designing it to hopefully make sure it's not going to break. Things do break and shake occasionally, it happens, but you know, it's a nervous moment, but you get through it. This is called moments of inertia. So they have this special table. It's kind of like balancing the wheel on a bicycle. They basically, you know how you spin a bike tire, and if it comes to a spot, you know that your tire's not balanced? They do the same thing on a big scale for our entire rocket. So they're figuring out exactly where the center of gravity on this thing is, and then they put some of the group back here at this table is working actively to analyze it and try to basically pluck the x-rays from the noise. And we're preparing to refly it again in Australia. We haven't received it back yet. It's on a boat, I think, what's today? The 11th? 14th. It should be in Los Angeles. So it should have arrived back and is now slowly making its way back to us. We'll get it back. Hopefully we'll be able to salvage some of it, and we'll be able to fly it again. That's about all I have. Do you guys have any questions? My son, what is your question?
Will a technical like be common?
No, don't do comments. Only questions.
Well, they're on the air.
Yeah. Anybody else? Go ahead.
What do you do for fun on that island?
Oh my gosh. So I didn't actually post. See, you feel slightly guilty. Oh, he was asking, what do you do for fun on the island? Well, so NASA actually has very strict work hour restrictions. Their people can't actually work certain amounts of hours. You know, they can only work so many days in a row before they are mandated a break, which is weird because we at university don't really play by those rules. So it was weird because we would work our faces off, and then basically everyone would be told to stop. And once they have ordnance, you know, like rocket motors and stuff, we can't even access the pad without the safety people. So when they shut down, we shut down. So we actually had a decent amount of time off, which was pretty cool. So there was fishing. For those of you interested, I can send you photos of fishing. Was incredible. There was snorkeling, scuba diving. You know, it was an island in the tropics. Now,
What's your favorite drink? Everybody's favorite drink?
that's right. I mean, there was a bar. It was weird because, you know, it's like the one bar on the island with everybody in it. But
Wasn't there a trademark drink that everybody?
I don't think there was a trademark drink. It was weird. It was, I mean, again, it's like a military base, so it felt like being in the States, but not being in the States. It was kind of surreal. I mean, it was weird. Like, you had all the things that you're used to, but sometimes not when you wanted them. Like, we had bacon the first week we were there, and we never saw it again, right? So they bring in all the food and produce from California somewhere. So it was a strange place for sure. And there's no civilians, there's no children. That's right. And it's weird that there's these big radar facilities. Some of the areas of the island are off limits. I didn't put it on my my slides, but there's a huge sort of military monument because it used to be a Japanese island, and there was a huge battle. All the sites are still there. You can go up to the pillboxes that are destroyed by naval artillery. They tell you not to dig because you can find unexploded ordnance and stuff like this. And it's a surreal place, but it was really neat and special. What else did we do for fun? I don't know. Worked and went in the ocean. That's about it. Any other questions? Well, thank you very much. It was my pleasure.